Hello and welcome back to this next segment in sample size calculation in R. Today we're going to be going over what I call the red tests, which are more complicated designs. So we'll cover different kinds of ANOVA, some different kinds of regression, as well as an foray into multi-level modeling. And I'll wrap up with just a overview of generalized linear mixed models, but we won't actually cover those here. So let's get started with repeated measures ANOVA. So this is sort of like a mashup of one-way ANOVA and the paired t-test, in which the paired t-test, the samples were related to each other, and ANOVA, there's more than two groups. That's in essence what repeated measures ANOVA is. It's going to be where you're testing if one mean is different among groups. The groups are repeated measures, so there's going to be something along the lines of, for our example question, is there a difference in blood pressure at 1, 2, 3, and 4 months post-treatment? So all of these are repeated measures because each sample is one patient, and then they get 4 different measurements across these time intervals. So to do this, it's a little more complicated than simple one-way ANOVA. We're going to be using the package WebPower and the function WPRM ANOVA. It's going to take a few more things here. Let's just start with the things we know about. So effect size, our alpha and our power, so that's going to be okay. Then let's go with these things up here. So NG is the number of groups. So we can do multiple different groups. And then NM is the number of measurements, multiple different measurements. So for our example here, we're just going to have one group. So we'll set this to be 1 for our examples. So it's just one group of patients, and then the number of measurements is, this is the repeated measures, 4 different measurements. Then we have this N score. It's the non-sphericity correction coefficient. We can get that by, if we have background data, by actually running a test. Otherwise, we can just assume it to be 1. And then there's type, 0, 1, and 2. Value 0 is between effects, 1 is for within effects, and 2 is interaction effects. So for our examples here, we're only going to be working with what we call within effect. That being what that means is within effects variability. It's the variability of a particular variable for individuals in a sample. So that's going to be among the repeated measures, whereas the between effects is differences between individuals. We don't really care that individuals have different individuals have different blood pressure here. We're really interested in is if individuals themselves have different blood pressure across these different repeats. So the effect size calculation is going to be, has a bit more going on with it. It's the ratio of the standard deviation of group means and then the overall standard deviation. Overall standard deviation is pretty easy, but the standard deviation means here it's going to be the sum across essentially the difference in group mean and the overall mean squared and then divided by the number of groups. So when we have to calculate this, we have to take this into account. But for our example here, let's just guess a small effect. For after test again, small effects are 0.1. And so again, this non-sphericity correction coefficient, so this N score, 1 means the sphericity is met. So we're just going to assume that it is for this, but obviously we can run tests when we have background data. So looking at this in R, we use that WPRM ANOVA. So the number of groups, we can just put null. You can also just not include this, and it'll still do the same thing. One group, 4 measurements, effect size, correlation coefficient, and then our alpha power, and then we're once again doing type in for the within effects. This gives us this for a total of 1,092 samples. And for this one now, it's different as opposed to the other ANOVAs, where it was per group. This is samples total. And again, that makes sense because we do have we just have one group, and the repeated measures are the same individuals, so we need 1,092 individuals, which will sample each 4 times. Okay, here are some practice for you. I suggest pausing this, working this out on your own before checking out the answers. Okay, let's dig into number 1, where we're actually given raw data. Looks like there's 4 different treatments or 4 different measures. So we want to get our effect sized. So I'm not showing a lot of the work here, but essentially for each of these, you need to get the overall mean, so taking the average of all of these, and then the group mean. So here's the group mean for the first group minus the total mean squared, and doing all this, and number of groups, then divide by the standard deviation, where you just get the standard deviation of everything. That gives us 0.608. Then I actually ran sphericity using ANOVA. I used this package EZ, so you can download that. And then in EZ, I called this just ANOVA 3, called it EZ, called this, so this was the package, this is the function, EZ ANOVA. I ran this. This is example 3 was I just made a data set of this data. And then serum levels, patients, and then within. And then I got this out. And so essentially we found that sphericity was non-significant. So coefficient was 1. So if sphericity is significant, it's going to be less than 1. But if it's non-significant, the coefficient is 1. So we had one group, 4 measurements, because just patients is the group, and then the measurements are these different months. And then within effects to give us 31 samples total. So just a quick note here, not everything in repeated measures has to be like by time, but that's just the easiest thing to example. With that in mind, let's look at our second one, where there's difference between 3 different months post-treatment. We're given no other information, so I'm going to just guess that it's non-significant, so a non-sphericity correction of 1, and then a medium effect. 3 measurements, type 1, plug that all in to get 156 samples total. Okay, we've made it to multi-way ANOVA, and I consider 2 kind of subsets of that. One is when you just have one category of interest, and the other is when you have multiple categories of interest. Let's dig into that, what that means. So in one-way ANOVA, you just had one kind of group, like gender, or sorry, no, that would be t-test, like age class, like infant, juvenile, adult, middle-aged. In multi-way ANOVA, you can actually have multiple different categories. For example, you could have your age class, and then you could also layer on gender. So you have 5 different age classes, 2 different genders, for a total of 10 different combinations. However, in this kind of ANOVA, where I say one category of interest, you only actually care about one of those categories. So maybe say your gender, but you want to control for your age class. So that other category we call control for. It's often called, sometimes you'll hear this as like blocking ANOVA, nesting ANOVA, random effects ANOVA. Kind of all kind of what I would call variables to control for. So let's piece together an example just to see what I mean. So is there a difference in treatment, drug A, B, or C, for a series of 4 different hospital sections, block 1, 2, 3, and 4? So what I'm asking here isn't, hey, is there a difference in hospitals? It's, no, I'm really interested in this drug, if there's an effect of it, but I know there's variation in these different hospitals, so I kind of want to account for that, so I'm not failing to see a treatment effect because there's so much variation in different hospitals. So we're going to be using web power again, and this is going to be web power, then K ANOVA, K as in like the number of groups. So we're going to need numerator degrees of freedom, and then number of groups, and just our effect size, alpha, and power like normal. So the number of groups here and the numerator degrees of freedom kind of come from our question. So since we want to control for sections, our numerator degrees of freedom is only the things that we care about. So our treatment, so that's going to be the number of treatments minus 1 equals 2. That is our numerator degrees of freedom. The number of groups, regardless of whether you're looking at one or more categories, is going to be just the total number from one group times the total number of another group. So 3 over 4 times 12. And then we're just going to, for here, we're going to guess a medium effect size. Now, if we have to calculate effect size, there's a lot going on here, but here is essentially what we'll do. It's the ratio of the standard deviation of blocking sections and the standard deviation of all groups. So the standard deviation of blocking sections, a kind of big equation where we sum up against the mean of each section across the overall mean and the number of sections. So kind of like what you saw for the repeated measures ANOVA. And then the standard deviation of all groups, treatment times section, is kind of big long, but you take the mean of each group and then the overall mean, and this group being each combination of treatment and section, so that's going to be 12, so that's a lot over the number of treatments and the number of sections. So a lot going on, but it's doable. But for our test here, we'll just do a median effect size of 0.25. Take a look at this into R, WP, K, ANOVA, plug in degrees of freedom, number of groups, F, alpha power, gives us a N of 157.3, so round up to a total of 158 total samples, and we notice here that they tell us sample size is the total sample size, so not per. If we divide this out, so 158 divided, we knew we had 12 groups, 3 treatments, 4 hospitals. That gives us, it's a little over 13, it's like 13.117. So we of course then have to kind of bump this up to 14. So that's 14 patients from hospital 1 with drug treatment A, and so forth. Okay, let's take a look now at multi-way again, but now with more than one category of interest. Maybe you are interested in more than one category. So we'll be using the same sort of setup, but we will put things in for the degrees of freedom differently. So another example here is, well, there's a difference in treatment, so A, B, and C, across age and cancer stage. So here, also we note I have 3 different categories, because you can do this for as many categories as you really want. Obviously, the more categories, the more sample size you need, but you can do it. And here, there's no indications that I want to control for these, but I actually care about this. So we know that our categories of interest are all 3 of these categories. So then our numerator degrees of freedom, we're going to have to take into account all of these. So we're going to take the degrees of freedom from all of them and multiply them. So 3 minus 1, 3 minus 1, 5 minus 1, 2 times 2, 2 times 4 is 16 degrees of freedom for the numerator. Then our number of groups, just all of them multiplied together. So 3 times 3 times 5 equals 45. So we don't have background information, so we'll just guess that there's a small effect size. And then again, if you need to calculate it, this is a little more complicated. This is the best I could find for how to get effect size calculation. We couldn't quite do what we did for the control, the only one category interest. This should be the eta squared, which is going to be the between groups variance and the total variance, the difference between the two, and then the square root of this eta squared. So we'll take a look at that later. Looking in R, again, similar to the only one category interest, we just plug in all our values, and we get here to a total of 1941 total samples. Again, we had, so 1941, we divide that by 12, or sorry, not 12, but 45, because we had 45 group combinations. It was us, I think it's 43.13, so we can round up to 44. So we need 44 groups for each of those. So drug treatment A for children with cancer stage is 1, and 2, and and so forth. All right, now that we've got a multi-way ANOVA out of the way, take some time to practice here, pause this, and you can work through it yourself. Okay, so this first one's a bit of a wall of equations, but let's work through it together. So we know we get the information raw here, so we have to calculate things ourselves. So we're going to get these two values here are different standard deviations, so it's this equation divided by this equation, where again J is the drug groups and then K is going to be the age groups. Big thing here is we're controlling for age, so we only want to focus on treatment. So for this first one here, this is the different drug groups, so the means divided by the overall means, and so forth, divided by the number of drug groups, which is 3, and then that's all divided by each drug, the mean of each combination. So drug A for children. So I think that's this first. I guess it's not this first mean here, but it's one of these means, and then divided by the overall mean, and you do this for 3 times 3 groups, because we had 3 drug treatments and 3 age groups. And if you do all of this, you get an F value of 1.74 divided by 2.65, give a effect size of 0.657. Numerator degrees of freedom, drug treatments minus 1 is 2, number of groups was 3 age groups times 3 drug groups, which is 9. So plug that all into WPK ANOVA to get 27 samples total, or just 3 per group. So we just need, say, 3 in taking drug C, adults, 3 adults taking drug C, and 3 adults taking drug B, and 3 elders taking drug B, and so forth. For 2, we're again looking at these things. We've seen this kind of thing before, looking at drugs, age, and cancer stage, and then we get some trial data. So it looks like we actually care about everything. So our 3 groups, our 3 categories are treatment, age, and cancer stage. So therefore our numerator degrees of freedom, since we had 3 3 and 5, it's 3 minus 1, 3 minus 1, 5 minus 1, 2 times 2 times 4 is 16. And then our number of groups is just 3 times 3 times 5 equals 45. Then we're actually given a lot of this information, so the between groups variance is 27.3, so we can just plug that into our partial eta squared equation, and then our total variance is 85, which is very handy because I would not like to calculate this ourselves. 0.32, plug that into this equation to get an effect size of 0.686, plug that all in, 68 samples, but to have even groups, we're actually going to need 90 samples. So you can think about this is we have a total of 45 groups. 68 doesn't go evenly into 45, so but 90 does. So if we put 90 into 90 divided by 45, that's going to give us 2 per group. There we go. Okay, let's take a little breather here and push on.